All right, so while we're unpacking our much-awaited pizza, I'll get to introducing the speaker for today. So this is Jordan Mirocha. Jordan did his graduate work at the University of Colorado, and since then he's worked at UCLA and McGill, and is now at the Jet Propulsion Laboratory in California. So today he'll be telling us about mapping the near-infrared sky with SPHEREx. Thanks, Jordan.
Thanks. All right, really happy to be here to visit you guys today to talk to you about SPHEREx. So SPHEREx is a NASA MIDEX mission aimed at mapping the sky in the infrared, as my title suggests. And I've been using, for the last couple of years, this beautiful artist's conception of what SPHEREx would look like in low Earth orbit, mapping the cosmos on the largest scales. And as of a month ago, I can show you a real picture, all right? So this is SPHEREx drifting away from the second stage Falcon 9 rocket on March 11th last month. And so I just wanted to avoid burying the lead here. If you remember nothing else from the next hour, just know that SPHEREx is successfully launched. It's undergoing its commissioning process right now, and its survey will begin very soon. So I'll tell you a little bit of that story today, but I want to mostly focus on the science themes of SPHEREx and the kinds of data products that it will produce that you might use in your own work. Okay, so this is our team. Like I said, we're a NASA MIDEX mission, so that's a medium explorer class mission. And we have very ambitious science goals, but we're still quite a small team, many of us located at JPL or Caltech. We can, for collaboration meetings, we can still fit in a room pretty similar in size to this one. And so I hope in the next couple of years you'll invite out some more of my colleagues to talk about the interesting work they're doing on SPHEREx. So I can share the slides afterward. I think you've already had at least one of our team members out in the last year to talk about ICEs. But our principal investigator is Jamie Bach at Caltech. Olivier Doré is our project scientist. And then we have involvement from all kinds of great people scattered across the globe. Okay. So this is kind of a one-slide primer on SPHEREx. All right. So SPHEREx is, if you haven't heard anything about it before, you might be surprised to learn that it is a 20-centimeter diameter aperture telescope. Okay, so it's a surprisingly small telescope, but it has an enormous field of view, almost 40 square degrees in a single image. So the primary mirror here, the primary aperture, sits within these nested concentric cones. These are photon shields that help to passively cool the telescope. So there are no cryogenics on board SPHEREx to keep the cameras cold. It's all passively cooled. Right. The spacecraft was provided by BAE Systems, the aerospace company formerly known as Ball. And then the detectors are the same ones that are used on JWST NIRCam. These are 2K by 2K near-infrared sensitive detectors, with one important difference, which is that sitting above each detector is what's called a linear variable filter. Okay, and these LVFs are really what make SPHEREx SPHEREx. Okay, so we like to compare ourselves to WISE. If you're familiar with WISE, it's kind of the previous wide field infrared survey telescope from NASA. Also surprisingly small aperture, kind of 0.6 square degree field of view. So our field of view is much bigger than WISE. And so our mapping speed, which is like a useful figure of merit for a cosmological experiment like this, our mapping speed is about 16 times larger than WISE. Okay, so I'll make a few other comparisons to WISE a bit later on. Also, I forgot to say this at the start, but feel free to interrupt me as I'm talking. We don't have to leave all the questions to the end. Okay, so let's talk a little bit more about these LVFs. All right, so what I'm showing you in this slide is a kind of cartoon representation of the SPHEREx focal plane. There are 6 detectors, and the color scale here is indicating the wavelength in microns that each pixel in each of these detectors is sensitive to. Okay, so you'll notice 2 things straight away, which is that the top row of detectors is kind of blue sensitive, and the bottom row is sensitive to the redder wavelengths. That's because there's a dichroic beam splitter sitting above these detectors that first divides the array into kind of a blue half and a red half. The second thing you'll notice is that along the vertical axis of each of these detectors, there's a gradient in the wavelength sensitivity. So you can imagine observing a single source and taking a series of exposures as it drifts across each of these detectors. And because each row of pixels has a different wavelength sensitivity, you are essentially piecing together the full spectrum of this object in a series of individual exposures. And as the telescope points slightly differently on each successive orbit, this source hits a different one of your detectors that has a different wavelength sensitivity, right? So this is just kind of a garden variety galaxy spectrum where you can see you're kind of slowly building up its spectrum to 102 points after 102 individual exposures, all right? So this is, if you're just interested in collecting spectra of a bunch of individual objects, this is not a very efficient way to do this. But one thing that this gives you is a spectrum of every pixel on the sky, not every source. And that's incredibly useful for a lot of the science that we're doing in SPHEREx. So to give you a sense of what this looks like in practice in the kind of context of our all-sky survey, I'm showing you a movie here of SPHEREx in orbit in Leo, first indicating its observing zone. So there's really just a few things that we have to avoid, like we don't want to look at the sun, we don't want to look at the Earth, and we want to avoid the moon. And these avoidance criteria give rise to a kind of semicircle observing zone at any given time. So what's being depicted here is a single one of these LVFs, just for illustrative purposes, but of course there are 6. And then you can see the color sensitivity as in the previous slide. And as you're taking a series of exposures, you can see individual sources, as expected, are kind of drifting along the vertical axis of the detector, and so you're piecing together their spectra. Every couple of individual exposures, however, in order to maintain these avoidance criteria, chiefly in this case, avoiding having the Earth rise up into our field of view, you have to take a big slew in order to stay in that semicircle viewing zone. So this leaves gaps, at least at first, in our spatial coverage, which might strike you as a problem. But of course, we're just continuing to do this 24 hours a day, 7 days a week, 365 days a year. And so upon successive visits on successive orbits, we do actually piece together full sky coverage in every pixel of the sky and in every spectral channel on the detector. Okay, so this whole process that's being dramatically accelerated here of mapping the sky takes 6 months. Okay, so a typical pixel in the sky will have 1 hit per pixel per spectral channel every 6 months. But you may have noticed something special about this scan strategy, which is that we actually pass through the ecliptic poles on every orbit, which means we naturally build up deep fields there. So this is a map now in galactic coordinates indicating the locations of the ecliptic fields, where because we're passing through on every orbit, every 6 months we actually get more like a couple of 100 hits per pixel per spectral channel. So the north deep field in particular is where we're focusing our extragalactic background light investigation. We would probably also try to use the south ecliptic pole if not for the Magellanic clouds, which kind of make a mess of this part of the sky, but that data might be very useful to you in your own work. It might be very useful for cross correlations with more distant targets as well. Okay. So what does this all mean for our sensitivity, given our scan strategy, our relatively modest telescope, and so forth? So what I'm plotting here is our limiting point source AB magnitude at 5 sigma as a function of wavelength. And so you can see a smattering of other points here from other wide field optical and near infrared surveys like pan-stars, like WISE, and like 2MASS. And so the main thing to take away from this is that, as expected, we're sort of comparable in sensitivity to WISE in our all-sky survey. That's our red points here. But the key point, of course, is that we have 102 spectral channels in this region rather than just a handful of photometric points. And our deep field sensitivity is approaching that of pan-stars in the region where we overlap in wavelength. So a nice, easy way to remember this is like if you've used WISE for your work in the past and you could detect an object of interest to you, we'll get a spectrum of it. All right. So yeah, keep an eye out for our data, which I'll say more about later. So one of the things that we'll provide to the community are catalogs of all kinds of different objects. We're expecting to detect over 1 billion galaxies with variations in how accurately we can determine their redshifts depending on source type and redshift and a variety of other factors. Clusters of galaxies, stars in the Milky Way, potentially high redshift quasars, certainly some quasars at low redshift, solar system objects. Already by eye in the raw data, we're seeing PAH emission from molecular hydrogen and shock-excited regions in the Milky Way disk, all kinds of crazy stuff. So I can't show you that yet, but just trust me, it's amazing, and keep your eyes peeled for some press releases on that stuff in the next few weeks and months. So fundamentally, also, we're going to make these maps available. And they kind of come in two forms. So the so-called spectral images, or the LVF images, where the wavelength dependence is still left in the image, will come out on sort of every other month timescales. And you'll be able to log into the IPAC server, the Infrared Science Archive. And basically, if you have objects of interest for your own work, you can type in their coordinates and see if we've yet observed that patch of the sky, and if so, you can extract whatever spectrum we have available. You could also get custom mosaics or like thumbnails of these objects, and just general kind of basic visualization of these fields. On slightly larger timescales, since it takes us a while to survey the whole sky, we'll give the community mosaics on a sort of roughly annual basis. And then on longer timescales yet, we'll have these catalogs that I talked about on the previous slide. And the idea with a lot of these more high-level products is that we'll revisit and reanalyze the data with each successive 6-month survey. So kind of in anticipation of the real data flowing in, around the time of AAS this January, we made available some simulated SPHEREx data products, the idea being that they are identical in every regard to the real data, except that they've been created with our sky simulator rather than the telescope. So the format of these files is identical to the real data, and they include all kinds of ancillary information like, obviously if you're analyzing these LVF spectral images, you want to know the wavelength sensitivity across the detector to do science. So that information is all included here. And you can use DS9 to visualize these images, and so on and so forth. So if you're curious about anything I'm talking about today, you have ideas about how to use this data in your own research, please do check out this website and see if you can start making sense of these images. And if you can't, let us know. We want people to use this stuff. Okay, so I want to transition into like an abridged story of SPHEREx from the kind of testing of the detectors in the lab at Caltech all the way to launch last month at Vandenberg. So these are a few of the real heroes of our team who went through painstaking efforts to test the detectors in the lab in the basement at Cahill. So one of the most important things about these detectors is understanding what wavelength each pixel in each array is actually sensitive to. So in the previous slide, you were seeing the kind of selfie off the window of the thermal vacuum chamber where the detectors were living for this test. And the basic procedure here was to shine in a monochromator, or just a tunable laser, at a single wavelength through the window onto the detector and mapping out which pixels were sensitive to that wavelength of light, right? So that's what's going to be shown in this movie. So this is just a band 2, so detector 2. And you're going to see this kind of arced shape move up through the detector as we scan through wavelengths. And then here you're seeing kind of like a 1D response of the detector. All right. So a few things you'll notice about this, and this is real data, okay, from the lab. The spectral band passes are peaking near 1. They're not quite top hats, but they're close. They're very sharply peaked. So that's good. The other thing you'll notice is that it's not a perfectly rectilinear sensitivity across a row of pixels. There is some curvature across the detector. This is just a byproduct of the coding I gathered from our instrument team used on the LVFs. So that's not a problem as long as we understand it. And these tests helped us understand it plenty well to account for this in the data analysis. So this is often referred to as the smile, though the convention here vertically flipped often leads to us referring to it as the frown. And this is just the broad, the full view across all 6 detectors, which are indicated with different colors here, showing that this kind of general behavior is consistent from the blue edge of the band to the red edge of the band. So once this was all said and done, our instrument team revisited our estimates for SPHEREx's sensitivity, which includes things about our scan strategy and exposure time, but also the kind of sensitivity of the detectors themselves, right? So at the time of the proposal of SPHEREx, the estimated sensitivity was kind of within this, this envelope where the upper edge is sort of the best case we could possibly hope for based on what we understand about these detectors and the survey plan at the time, and so on and so forth. And the bottom region, this boundary that's about a half magnitude shallower, is a more conservative estimate where maybe some things don't work out quite as we hoped, but this is still sufficiently good to meet our science requirements. So with these new data from the lab, the instrument team revisited our point source sensitivity and found that in bands 1 through 4 we're at or above the best we could have hoped for just a couple of years ago. So that's really good news. In the longer wavelength bands, we're right kind of in the middle of expectations. And of course, very importantly now, the uncertainty on how sensitive we are has dramatically shrunk. Right? So this is all great news, especially in bands 1 through 4, potentially a factor of a few times more sensitive than we hoped for. So after this exhaustive lab testing campaign, yeah, go ahead, question.
Sorry, it's on the former slide. Why does the yellow and green dip like that?
Like at the edges?
Yeah.
Yeah, so there's a bit of funny behavior on the edges of the detector. I think part of that is just natural, and we have we're probably not going to use the very edges. There's some roll-off in the sensitivity. I think part of this also has to do with the beam splitter that is dividing, so this is the blue half. This is like the top row of detectors I showed earlier on, and this is the bottom row. So at the kind of bottom and top of each of those arrays of detectors, you get a little funny business from the beam splitter. Okay, so after, yeah, sorry, one more.
So if I understand correctly, this is all lab characterization, right?
This is all what?
This is all data from lab characterization.
So it's the data from the lab coupled with the latest survey plan that includes information about the exposure time.
Yeah, I was wondering if you can comment on how does this compare with the on-sky actual calibration.
So this is for the all-sky, not the deep field.
Oh, I'm asking, since you guys have flown, I was wondering if there's actually on-sky measurement that compare with this estimate.
Oh,
from
not
that.
yet,
Okay.
not yet. But yeah, that's a good question. I can say that roughly in the rough preliminary tests with early images, the brightness of the images is very close to what's expected. I have one example later where we can kind of eyeball it, but I don't have that in this kind of form. Okay, so after the detectors were characterized in the lab, they were shipped off to Boulder, Colorado to be integrated with the telescope and the spacecraft, which you're seeing here. So we've got a person for scale here, and you can see now our very shiny photon shields keeping the telescope cool. You can see it's got a dust cap on top to prevent particulates from getting into the telescope. And we went through yet another series of exhaustive tests in this huge thermal vacuum chamber, which I don't have time to go into in much detail, but basically, things went really well. As per usual, there were some bumps along the way, but those were all sorted out by our team. And then SPHEREx was packed up on a truck and hauled back to California just in January of this year, where it was kind of taken out of the truck and reassembled at Vandenberg Space Force Base. This is just a couple hours north of Los Angeles. And once, so the next step was basically to get this thing into the fairing that it was going to be launched on. So you'll see SPHEREx here now inside of the Falcon 9 fairing. What's cool about SPHEREx, the fact that it's kind of this small payload, we actually shared a ride to low Earth orbit with the heliophysics SMEX mission called Punch. So we got kind of 2 launches for the price of 1 here. And I think this is actually the first time this had been done with NASA missions before. And then off to the launch pad, where it sat for a little longer than we wanted. So we were supposed to launch on February 28th of this year. And when that started to look like it was not going to happen, some Caltech grad students got to work trying to estimate when this thing would actually launch in a very data-driven way. So people did this around the time of JWST's launch, but what you're seeing here is basically the predicted time until SPHEREx launch versus the actual date. So on February 21st, we thought we were going to launch in 7 days. But then there were kind of continual revisions of our launch date due to a variety of factors, most of them not in our control. And so a series of updates to this forecast ultimately projected a March 10th launch date, which I think we would have actually done if not for the bad weather. So then we slipped to March 11th. We were all freaking out, obviously. There was a government shutdown looming at this point. The weather was looking like it was going to be complete garbage for the couple days after this. So people were, trying to take their minds off of things by the launch site. So this is Richard Feder, a former Caltech grad student, who noticed that if you zoom in on this picture, you can actually see SPHEREx on the launch pad, which is pretty cool. So I will say, having not visited this part of California before, it's actually a pretty beautiful area, a lot of great wildlife, hiking, beaches. There's an ostrich farm, there's great wineries, and you can go skydiving. So 10 out of 10 would recommend. So this is the view that we had, not from the base, but from the airport nearby, just standing on the tarmac at sunset. This is an incredible time-lapse photo taken by ASU grad student Pao Yu Wang. What's really cool is you can actually see the first stage rocket here separating from the second stage and peeling back around to come back down and land. So before this, I was still under the impression that all of these first stage rockets land on a barge in the ocean, but that's actually not the case. Some of them come back to the launch site and land, which ours did. And that is a truly surreal experience because it just feels like a rocket is headed towards you, like way faster than I was expecting. It's crazy loud, but it all went well, and the first stage landed back successfully at Vandenberg, I think about eight minutes after launch. And of course, SPHEREx continued on its merry way on the second stage rocket, and then about 40 minutes later, separated from the second stage launch vehicle, which had this really great view of it drifting off into its orbit. Okay. So, skipping ahead a couple of weeks, we had first light and an associated press release on April 1st, not a joke. And here you're seeing again our array of detectors, the different color bar, but the same idea being that we're indicating the color, the wavelength that each pixel is sensitive to. And this is the real sky now. And a few things you can notice straight away is that the detectors work. That's good. These images look like astronomical images. Can also tell that the telescope is in focus, which is a huge relief because this is not something we could adjust after launch. So something I skipped over is that there's a very exhaustive focusing campaign at JPL, where basically in the laboratory, the focus was adjusted, take it to JPL, simulate the conditions of launch in a vibration test, take it back to the lab to make sure the telescope's still in focus, do it again. And you know, we were pretty confident that the telescope would stay in focus, but you're never quite worry-free about this kind of thing. So seeing these very point-like stars was a huge relief when these images started pouring in. And there's a lot to marvel at in these images. You know, we can see nearby galaxies, we can see much more distant galaxies, and we've been trying not to distract ourselves too much in the last few weeks, just staring at these things as they come in. You'll also notice this helium air glow line, which is a little stronger than expected, but seems to come and go in amplitude a bit depending on our exact position and orientation and what the sun is doing. So a couple more images. This is one through the galactic center. This is actually the same field of view, just in two different SPHEREx bands. So in the shorter wavelength bands, this is sort of like 1.5-ish microns, plus or minus. You're still getting a lot of attenuation from dust in the plane of the galaxy, but at the longer wavelengths, this is sort of 4 to 4.5 microns, you start seeing straight through the dust. So despite the fact that we're, by most Hubble or JWST people's standards, a low spatial resolution instrument, we still can produce some pretty staggering images, I think. I just want to give a quick shout out to Brendan Krill, who's our pipeline architect. Something a few folks on the team started doing when the images started rolling in is to compare the real images to the ones that we predicted using the SPHEREx sky simulator, which Brendan Krill is the architect of. So if you just do a quick by eye comparison left and right in each of these images, I think you'll agree this is pretty great initial agreement just at a glance. And this is still like electrons per second, so like there's a lot of processing and stuff still to be done to these images, but just a quick and dirty check was very encouraging. Okay, so I'm gonna switch gears now to talk more about the science we're doing in SPHEREx, starting with the two science themes I don't actually work on, so I'll cover those in just a few slides, and then I'll try to spend more time on the extragalactic background light towards the end. But feel free to ask me questions about this stuff. And like I said earlier, it'd be great to get out other folks from the team to go through these things in more detail. So one of our science teams is focused on cosmic inflation. Okay, so this is the period of very rapid expansion in the early universe that CMB experiments are trying to constrain with B modes, but that we are trying to constrain through large three-dimensional clustering measurements, essentially. And so one of the main parameters of interest is this parameter FNL that's taking on a highly exaggerated value here, which basically characterizes how non-Gaussian the primordial fluctuations are. So you can imagine if you have a very non-Gaussian tail of fluctuations in the early universe, the structure in the late time universe is a bit more patchier and you have a higher degree of clustering in galaxies in any given field. But if the PDF of fluctuations is really Gaussian and FNL is 0, you see this more smoothed out picture. And so the key to doing this kind of measurement is to be able to measure the locations of these galaxies really precisely, not just in RA and DEC, but of course along the line of sight, because that opens up all these long wavelength modes that are really sensitive to inflation models. So this is where SPHEREx's spectrophotometry capabilities really come into the picture. So what I'm showing you here is an example spectrum of a kind of ordinary galaxy in the near infrared. This particular galaxy has a strong PAH emission line that we resolve with a few elements, but is otherwise basically free of emission line features. So you might think, well, like, how do you measure the redshift of this object? If you didn't have this line, for example. So if you just had a few broad photometric bins spanning this range, like you had Ys 1 and 2, maybe you had some 2 mass points, you could get a very rough redshift of the source. But if you have 102 bands from SPHEREx covering this range, you can really see all these little bumps and wiggles in the continuum, the most prominent of which is this 1.6 micron feature. And that's really the workhorse of measuring redshifts with SPHEREx. So this is a paper led by Richard Feder, our skydiving friend from a few slides ago. And long story short, we think we can do this measurement pretty well. And so people have been trying to constrain FNL with CMB. I'm also showing here the running of the spectral index. And that's a pretty tough game because the CMB is a 2D surface, so you're limited in terms of the largest scales that you can measure. And so opening up the kind of third dimension with SPHEREx can in principle yield very tight constraints on this parameter FNL, especially if you're able to combine power spectrum and bispectrum measurements in your likelihood. So the tightest contour here includes power spectrum and bispectrum. That's a very difficult measurement to make, but it's a very powerful one. Okay, that was my quick tour of cosmic inflation. I'll do a similarly quick tour of ices, and I heard at lunch that, or I guess at breakfast that immediately preceded lunch, that you had Gary Melnick out not too long ago to tell you about ices. But in case you missed that talk, or in case your memory is a little fuzzy, I'll just remind you that, for the cosmology and the EBL analyses in SPHEREx, we're really avoiding the galactic plane. And so the fact that we have a science team in our collaboration that's using those pixels as their science targets really means we're using every pixel in our survey to do interesting science. So that's kind of a nice aspect of SPHEREx as well. But the basic idea here is to look along the sight lines to background stars and measure the absorption along those lines of sights to try to infer the abundance of various ice species, most notably water ice and CO2 ice and methanol ice and a few of these other species. And so this is really, really cool stuff. I guess planets, people are pretty convinced that most of the water in the galaxy is actually living in ice. And so SPHEREx is going to provide essentially a map of the ice content of the Milky Way. And I think it's really complementary to JWST, right? So JWST is observing the same spectral range with much higher spectral resolution and can offer us very exquisite spectra along the same kinds of sight lines, but it's a very small field of view telescope, right? And so even in a kind of 20 or 25-year lifetime with JWST, it's possible that there's only hundreds or maybe thousands of targets that you can study in detail. With SPHEREx, because we're covering the whole plane of the galaxy and the whole sky, we're expecting more like 10 million targets. And of course, our spectral resolution is poorer, and our spatial resolution is poorer. But you can kind of think of this as a potentially very useful finder scope to map out where the interesting structures are and roughly how much ice is there, and then follow up with JWST. And these are sources in all kinds of different environments as well, as quantified by the extinction. All right. So in the last 10 or 15 minutes, I want to talk about the extragalactic background light. Okay, so this is basically all the light that's originating from outside of our galaxy, whether or not it's resolved into sources that we detect, that we resolve, right? And so the name of the game here is intensity mapping. So rather than trying to study the structure of the universe by finding bright galaxies and, for example, measuring their clustering or their individual properties, we're trying to measure the intensity field because the locations, the bright galaxies, do trace out this large-scale structure, but they're very biased tracers of where the light is, right? You can see that depending on the depth of your survey, the galaxies you see may just be the tip of the iceberg in terms of the total light production in the universe. So by studying maps like this, like we're going to make with SPHEREx, you can learn a lot about galaxies, even the faint ones that you'll never detect directly in a survey. So this is really, our third science theme is galaxy formation. And again, the fact that we have 102 maps at different wavelengths is extremely useful in this context. So the fluctuations, we're mostly studying fluctuations in these maps. You could also study just how much light there is in kind of a total intensity mode. But our focus is really on the fluctuations, and so we're sensitive to anything that clusters and produces fluctuations in these maps, which means galaxies. We're in principle sensitive to galaxies all the way back to the EOR. We're also sensitive to diffuse emission. So in regions where you have, in groups or clusters where you have lots of interactions, tidal stripping and mergers, and stars get flung out of their host galaxies, we know that can produce a low surface profile of emission that's quite large on the sky, but is very hard to detect in a conventional survey. And so we're very sensitive to that in a statistical way. And there might be fun surprises here. If, for example, dark matter annihilates or decays, that should have some clustering pattern as well, and may produce emission at the wavelengths of where we have known emission lines. Okay, so there might be fun searches for that kind of thing coming as well. So, and I'll just remind you, if you're not a galaxies person, that when we're studying star formation in galaxies, we're often relying on strong optical lines like the Balmer series lines, H alpha, H beta, oxygen 3, oxygen 2, and then if we can get it, Lyman alpha. And these lines are all captured in our band across a very wide redshift interval. So we're primarily using these rest optical lines at low redshifts out to reionization, and then starting at redshift 5.5 or so, we start to pick up Lyman alpha in our first band, which means that these intensity maps should be very informative with regards to star formation in galaxies. And I should say that we're not the only game in town in terms of studying this part of the sky or trying to learn about galaxies back at the EOR from data sets like this. We have 100 square degrees focused on the North Deep Field that has increasing coverage from other campaigns. So one of Euclid's deep fields is in the NEP. There's a Subaru program up there. DESI has started to observe the NEP as well, and there's, of course, archival data from Spitzer and WISE as well. And what this means is that not only can we kind of study our own maps in isolation by performing autocorrelation studies, we can cross-correlate with these galaxy samples to try to piece together the redshift evolution of the EBL as well. I'll say more about that in just a second. And I won't have too much time to talk about this, but we can also cross-correlate our maps with other maps in our library. So SPHEREx cross-correlations, which can be useful for a variety of reasons. All right, so within SPHEREx, it's really my job to build models that help us invert these kind of unintuitive measurements of fluctuations in a map and turn them into some kind of useful constraints on galaxies. And in principle, we're sensitive to all galaxies everywhere in the universe at a huge range of redshifts, diffuse light from stars that are no longer in galaxies. This is one of these problems, like many, that can kind of become arbitrarily complicated. And so we're trying to pursue a few different ways of doing inference with these data. And just to build intuition a little bit, to give you a sense of the problem we're dealing with, I'm starting with, here I'm showing you an example of a purely empirical model for the EBL, where the idea is basically, we have there's a long history now of conducting galaxy surveys across the electromagnetic spectrum, and one of the kind of easiest things you can try to measure is just the density of galaxies, so number of galaxies per square degree on the sky as a function of their AB magnitude. And if you integrate this curve, potentially with some extrapolation at the faint end, you're learning about how much light there is in the universe. And so in this particular paper, this particular fit tells you that about half the light in the universe comes from objects brighter than about 20th magnitude, which is roughly our all-sky depth, which means in the all-sky survey, we're probably missing half of the light in the universe, meaning it's in this phase that we can't actually resolve into individual objects. All right, so this kind of thing is extremely useful for coming up with like the total light inventory of the universe, but it doesn't immediately tell you what the fluctuations at these wavelengths should be. For that, you really need to have a model for how galaxies populate dark matter halos, and you need to have a model for how dark matter halos are clustered in the universe. So I've been pursuing a kind of semi-empirical approach, which I think has two key advancements. So the first of which is that rather than anchoring it to galaxy number counts, where you've made no effort to know the redshifts of the galaxies, what type of galaxies they are, anything about their properties, I'm anchoring to things like luminosity functions, stellar mass functions, galaxy color distributions. all in the context of a lambda CDM cosmological model where I know the abundance of dark matter halos, right? And so if I parameterize the things I'm ignorant about, which is basically how efficiently galaxies are forming in different kinds of halos, what are their stellar properties, how much dust do they have, I can build a model that matches the data that we already have, that's always going to be incomplete at the faint end, and I can build in flexibility in the model that allows me to explore different possibilities for the EBL, right? So, these three toy models here all describe this data pretty well, but will have very different total light production and fluctuations as a result. So that's the basic approach here, and we've got a model like this working. I'll just show you a few examples here. So these are a couple of different stellar mass functions, so just space density of galaxies as a function of their stellar mass at some redshift. And these models I've been building have all different kinds of galaxies. So we've got star-forming galaxies in blue, we've got quiescent galaxies, and then we have contributions from both centrals and satellites, which is really important for understanding the L dependence of our power spectra. And then, this is a mass function, so the luminosity functions, which are a proxy for the star formation rate, we can also match quite well over a broad range of redshifts. And as a sanity check, we can actually revisit what our model predicts for the galaxy number counts. This is a way of testing whether or not our SED modeling is really doing what we hope. And this is basically the same plot I showed you a couple slides ago, where we have galaxy number counts as a function of magnitude. And I have the models are fitting this extremely well. And now I can actually tell from the model what redshifts are contributing to these different magnitude bins, what kinds of galaxies are contributing to these magnitude bins. And that gives us a lot of power in trying to decompose the various contributions to the EBL. So let's look at the EBL itself finally. So what I'm showing you here is a prediction for the EBL power spectrum as a function of spherical harmonic L. And the top axis here is indicating the wavelengths at which we have maps, right? So we can do this exercise on 102 different maps. We could make 102 different curves like this. And so qualitatively, we generally get something that looks as follows. So on small scales, as L is getting large, we have shot noise, just due to the discrete nature of the sources giving rise to the emission in our maps. But eventually, we transition into the so-called two-halo regime, or where we're really just seeing the large-scale structure of the universe. And here, we're sensitive to the bias of the galaxies and the amount of light that they're producing. And we can look at how these power spectra change as a function of wavelength. If I wiggled around the knobs of my galaxy evolution model, these curves would wiggle around as well. Something I'm not showing you here is we can also cross-correlate our maps with themselves, which gives rise to about 5,000 other measurements that in principle we can use to constrain models. So we can also look at how these fluctuations, where in redshift these fluctuations are coming from. So as you might imagine, most of the power is coming from galaxies at low redshifts. But contributions from redshifts greater than 1, 2, 4, and even redshift 6, so EOR galaxies, are non-trivial here. So the EOR is kind of our ultimate target. We'd like to extract the signal statistically, and it's kind of a 1% level modulation of the fluctuations. But you can see it has a different shape as a function of L. And as I'll show you in a minute, it also has a different spectral shape, as do the low Z contributions, as expected. But before I do that, I'll just remind you another powerful thing about this technique is we can figure out what kinds of galaxies are giving rise to these fluctuations. And so these kind of four source populations I alluded to earlier, we have star-forming and quiescent galaxies, we have central and satellite galaxies, are kind of all important, actually. So if you built a model for the EBL just based on the cosmic star formation history, for example, you would not be coming up with all of the near-infrared light in the universe, to better than a factor of 2 or so. And if you neglected satellites as well, you'd be missing a lot of important fluctuations on small and intermediate scales. Okay, and then this is kind of one of our go-to plots for our kind of ultimate goal of constraining EOR galaxies. So I'm once again looking at the power spectrum, but now rather than showing the power spectrum at a single wavelength, I'm picking a single L-bin, so a single mode in the power spectrum and plotting the power as a function of wavelength. So once again, I've focused on the redshift decomposition of these fluctuations. And you can see that the contributions from different redshifts have different spectral shapes. That's because, intrinsically the properties of galaxies are evolving with time, but they're also, redshifting through different parts of our band. And so by the time we get to reionization, we have a very sharp feature associated with the Lyman break. Okay, so high-Z galaxy searches have been using the Lyman break for a long time to find individual high redshift sources. Here, we're seeing a Lyman break due to the entire population of galaxies during the EOR, which is pretty amazing. And the gray kind of staircase here is our expected uncertainties after the full 2-year survey. Okay, so we have, CMB people will be familiar with, component separation problems. We have the same kind of problem, but we're quite optimistic that because we have so many spectral channels and because we have so many modes we can measure, that we can actually disentangle all of these different contributions to the signal. And there's some proof of concept calculations, at least, that support that idea. So I'm starting to wind down here, but I just want to show you a few more examples of this modeling framework I've been building. So one way that we've been putting it to the test is to compare it to real data that exists now. And so what you're seeing here are a bunch of recent measurements from CYBER. This is a sounding rocket experiment operating from 1 to 2 microns. That is an EBL experiment that's been flown a number of times now and is very much a SPHEREx pathfinder. And this is just like 5 or 10 minutes of rocket data, actually. And so the blue curves here are the predictions of the model I just described. We also are expecting fluctuations, from stars in our own galaxy. And then the diffuse galactic emission, which is represented by these gray curves. And so in the kind of small scale limit, this kind of combined model is agreeing quite well with these relatively shallow measurements. But as we go to larger scales, there's actually quite a big gap that's opened up between the measurements and the model predictions. So we're not the first people to notice this. This has been talked about in the context of Spitzer and Akari measurements as well, and even some intensity mapping measurements using archival Hubble data. And there are a variety of explanations for this, some mundane, some very exotic. One of the explanations we tend to like in our group is that this is this diffuse emission that I alluded to earlier in the outskirts of galaxy groups and clusters that you just have a hard time constraining in a conventional survey. And so if you, we in this paper wanted to focus on the null hypothesis, which is just like the EBL as if diffuse emission did not exist, and see if we could rule out that null hypothesis, which we do at high significance. But this excess power, if it is really IHL and has nothing to do with the CYBER instrument or its deployment on a rocket, we should see it in SPHEREx immediately. So one of the members of our team likes to always remind us that SPHEREx is doing about 600 CYBER experiments per day for the next 2 years. So we're going to have much more sensitive data to look at with this very soon. Yeah, and then I'll wrap up by highlighting cross correlations. I think people here are interested in this in other contexts as well. But the basic idea is, the lack of redshift information in the raw maps, like photons don't tell us what redshift they came from, which makes life very difficult. Means that if we want to separate all the components of the EBL just with autospectra, we need to do a lot of modeling or have some kind of joint likelihood framework where we constrain different redshift pieces of the model. We can also just cross-correlate with galaxies at known redshifts to try to piece together the evolution of the EBL. And so when you do this, you will get some noise just due to chance alignments of foreground and background structures. But if you have a large enough area and a large enough catalog of galaxies to cross-correlate with, you can actually reliably recover the bias-weighted EBL from a particular redshift. And what that looks like in practice, this is a measurement that we're going to do with real data. is this is sort of like the color of the EBL plot I showed you with the EOR signal a few slides ago. If you cross-correlate with galaxies at a series of different redshifts, once again, you can see the interesting evolution in the continuum of the whole galaxy population, but at our native spectral resolution, you can actually also start picking out spectral lines. So these are the Balmer lines, oxygen lines, and Lyman alpha starting to come into our band at high redshift. So this is a measurement we can actually do with our data in cross-correlation with DESI or Euclid or whatever we can get our hands on, even our own catalogs, and should provide really powerful constraints on galaxies over a wide range of redshifts. So I'm running out of time, and I already mentioned our sky simulator. It's quite mature. But my colleague Ari Sukerman at Caltech has put together this kind of like nice flow chart of what all goes into a single simulated SPHEREx exposure that we're trying to account for in our analysis, starting from dark current and read noise in the detectors, photon noise from the sky, which is dominated by zodiacal light, the galaxy, stars, ZODI, and eventually the EBL as well. So we can actually simulate skies that have all of these components now. We can perform a mock component exercise, component separation exercise, including things like averaging and trying to understand systematics, and rinse and repeat to try to convince ourselves that we can actually do this with real data. So that's basically where we're at now. We have a pretty mature sky simulator, and we're starting to really run end-to-end simulations in anticipation of our first sky surveys being complete in the next year. So I will stop there, and I'll just remind you that we're doing this commissioning period right now. It'll wrap up in about a week, at which point the real survey will begin and data will start flowing out to the community 2 months after that. So I hope you'll keep your eyes peeled for SPHEREx data, and yeah, I'd be happy to take any questions. Thanks.
Sorry if I missed this, but what kind of detectors are in SPHEREx? And also, what are the logistics of characterizing something with 102 different wavelengths?
So I am not an instrument guy, but I'll do my best. This alphabet soup describes our detectors. I think these are the same exact detectors that are on JWST NearCam, right? So they're just near-infrared CCD-like detectors. Your second question was about characterizing the spectral response. Yeah, that was a painful effort, I think, scanning through row by row of the detectors with this tunable laser in the lab in the thermal vacuum chamber and analyzing the images that came out. That was a many months long campaign of round-the-clock work by our team. So yeah, without these guys here, we wouldn't be where we are now. So it was really important work. Yeah, I think it's literally pixel by pixel, row by row, going through the detectors to characterize the response.
Thank you.
In the back.
So you said that you could probe redshifts pretty accurately. Up to what redshift can you probe?
Yeah, it's a good question. I don't think I have a plot for this, but if you look at the kind of number of galaxies per square degree we're expecting to detect with SPHEREx directly, those curves tend to peak at about 1 or 1.2. But the tail goes out to maybe redshift 3. So it depends a little bit on how you select objects and how tolerant you are. Like there's always trade-offs with, you could consider fainter objects, but you might run into problems with confusion, and the uncertainty on your redshift might get worse. So there's a trade-off there in having more objects, but then potentially worse redshift accuracy. But just going from memory, I think some of the latest estimates put the tail of that distribution out to about redshift 3. We might have tens or hundreds of objects per square degree out to redshift 3 or so.
Follow-up question: how are you releasing that data? Is it in the same formats as you mentioned, or is there like a catalog that you put out?
Yeah, so I don't know yet about the catalog formats, but the spectral images are just SPHEREx files with a bunch of metadata, and so those will be available. If you just go to the IPAC website, there's like a little tab, and you'll be able to find SPHEREx data pretty easily that way. I'm assuming our catalogs will also come out through this same portal, but I don't think there were any catalogs included here. These are just spectral images. So. Yeah, Srini.
Yeah, thanks, Jordan. Can you say a little bit about the internal cross-correlations?
Yeah.
So are you talking about like cross-correlating with the internal galaxy catalog or different cubes?
So, this isn't quite what you're asking, but so this is what I would call an external cross-correlation, right? So if you take our maps and you cross-correlate with galaxy samples at known redshifts, if you looked at, you could, for example, if you had galaxies at redshift 1 and you wanted to study H alpha, you could pick our map at 1.3 microns, and you'd see the same qualitative behavior in the power spectrum. You could look at the cross-correlation of all the maps where you'd see these lines popping out, or you could just form the full matrix of cross-correlations, which is what I'm showing you here. So what I meant by internal cross-correlations is really, if you don't have an external galaxy catalog, you could also just form a matrix of cross-correlations between all of our maps with each other, right? In which case you would have, along the diagonal would be the autos.
Right.
And on the off-diagonal elements would be the crosses of different channels.
Right, but wouldn't that just pick the continuum? Wouldn't that just pick the continuum mostly?
It is mostly continuum, but it is a nice, if you can filter out the continuum, it's a nice way of seeing the lines, because you do get streaks like this emerging in the off-diagonals, because you can, if you pick the channel that has H alpha and you cross it with the channel that you think that should have H beta at some redshift, you get more signal, right? And so I thought I had we've been doing this in simulation a little bit. I think this is easier, but the internal crosses might also just be a nice way to diagnose some like problems with the data. So we haven't actually, Yunting Cheng has a paper, I think from last year about this, where you can see some examples that kind of look like this.
All right, thanks.
I have a question. So you mentioned this is a 2-year event. Could it go longer? And another question I had was, if a unique phenomenon occurred in space, do you have any provisions to break your pattern and look at a specific spot in space at a certain time?
Yeah, great question. So the first question is that the nominal mission lifetime is 2 years, but because we don't have any consumables that are required to keep the detectors cold, in principle, it could keep running longer if there was support to do so. The only limiting factor is the orbit, which will be fine for about 20 years. The telescope can point. There's reaction wheels that control the attitude of the telescope and all that stuff. Though the survey, so we've had some discussions about this. I don't know that I have a final answer for you. Probably relatively soon, conversations about what you might do with more time will start happening. A lot of missions have some kind of guest observer program that emerges. We may do something like that, though it is more difficult for us to dramatically change the survey plan because of the orbit we're in. You could think about doing minute adjustments to how the telescope's pointing as long as you don't stray outside of this observing zone. But the prospects for building up a very deep survey in a very specific part of the sky, I think that's going to be pretty tricky. But you might be able to, slightly retarget with some clever maneuvers to targets of interest or something like that. So those conversations are starting to happen now. But yeah, I think long story short, we would love to just let SPHEREx keep doing what it's doing and build the depth and do 2 surveys a year for 20 years. that would be a pretty incredible data set. But yeah, if we'll be curious to hear ideas about how people might suggest we change things in the next year or so. So if you have any ideas, let us know. Yeah.
Line of sight direction?
Yeah, so the question was basically, have we thought about using line of sight modes in the EBL fluctuations? That's a pretty tough game. So I think, so the cosmology team is essentially using line of sight modes, right, for the FNL analysis. I don't think we've made any plans to try to do the cross correlation in more than 2 dimensions. I think we really have focused all of our efforts on just taking a map, computing its power spectrum in whatever crosses we can. I suspect, we'll have the same problem as, for line intensity mapping experiments that have much higher spectral resolution than us. Their, K-perp axis is very big. And so if you're thinking about cross-correlating with SPHEREx in that same kind of K-perp, K-parallel space, I think it won't be quite as bad as trying to cross-correlate with like a photometric galaxy catalog where you really only have like the bottom brick of modes. We'll have a little bit more on top of that, but yeah, it might be worth thinking about some more. It's a good question.
What is the cadence of observations in deep fields? You mentioned SPHEREx will scan the entire sky every 6 months. So what is the cadence in the 2 poles?
What is the cadence?
Yeah.
Yeah, so some spectral channels are observing the ecliptic poles on every orbit. I think this this is a confusing plot, but I think it kind of speaks to your point. So what's being shown here is like all of our spectral channels, and then every point here is a hit for 2 different fields of view. So like if you focused on, so the blue points are if you focused on a patch close to the ecliptic plane, where, over the course of a year, like I said before, every pixel gets 1 hit every 6 months. So you can kind of see that, you mostly get all of the spectral channels within 10 or 15 days of each other. And then again, 6 months later. But if you pick a point in the north ecliptic pole, you get this orange coverage map, right? So you are potentially getting hits every day in some spectral channels, but like one spectral channel might get a hit today, not tomorrow. But then again, the next day, it's just kind of complicated.
Yeah.
So yeah, some of us at lunch were talking about like, could you do transient stuff with SPHEREx data? And the answer is like, maybe. Especially if you're interested in the ecliptic poles where we have this pretty good time cadence. It's just that, yeah, you're not going to get all the channels at the same time. But if you can make use of that information for something, it might be super cool.
Yeah. So another question is, if you bin like many many spectral bins,
Yeah.
how large is the improvement in terms of the depth?
Yeah, so things definitely get better. Where did that go? Yeah, so I can't remember if I remembered to emphasize this point, but this sensitivity curve assumes that we've binned 102 spectral channels into 10 broadbands. The reason for that is that if we kept to the native spectral resolution, where you'd better resolve this kind of bump and great stuff like that, the sensitivity is worse by order of factor of 10, or is it root 10? At least a factor of a few times worse, in which case your ability to detect the EOR is probably not going to be there. So I think like one of the best reasons to keep observing, if we can, there are many, is if we could do this at the native spectral resolution, that would be extremely useful. Not just for this kind of science, but for all kinds of things, right? So, yeah.
Thank you.
Yeah.
On the Z1, Z2, and Z4 bands, which lines do you use? Is
So
it like the sum of all the bands, of all the lines you could see at this redshift?
all the light, yep. So no effort's been made here to separate out lines from continuum. We're starting to experiment with some continuum subtraction techniques, which is actually pretty easy, seemingly, in these kind of cross-correlation matrix spaces, because you know exactly where the lines should be, right? So you can fit some kind of smooth template to the pixels left over. But I don't, yeah, it's still an active area of work. The continuum is very informative as well, obviously. It's just more mixing of the redshift information, so I think ultimately we'd like to use both.